Welcome everybody to the Digital Materials R&D session. In my presentation I will show you GeoDict's latest and greatest features for different fields of material research. My name is Martina Hümbert, and first I would like to introduce myself. I studied mechanical engineering at the University of Kaiserslautern. Then I did my PhD at the Institute for Composite Materials, also here in Kaiserslautern. In 2019 I joined Math2Market as business manager for Digital Materials R&D. In my talk, I will introduce impressive new features of GeoDict 2022. Most of them are further developments of some of GeoDict's greatest functionalities. We packed our module GRIDGEO with new geometries for our clients from additive manufacturing. People who do mechanical simulations should try the new user-defined downsampling factors, which help you to speed up your simulations. Shorter runtimes are also enabled by the conjugate gradient solver, which is now available for nonlinear simulations. It does not only make your simulations faster, but in some cases, such as the prediction of damage in composites, even more precise. Another great new feature are triangular struts in FoamGeo. I will show you how to use them to build a digital twin of a metal foam. And finally, the post-processing of FIBERFIND-AI has improved a lot, and I will show you how to profit from that by using a composite scan as an example. So let's start with the structure generation for additive manufacturing using GRIDGEO. Many conventional processes, such as injection molding, melt blowing, or foaming, lead to random structures. These can be modeled really well in GeoDict using modules like FiberGeo or FoamGeo. A big advantage of additive manufacturing is that you can control the microstructure of your material. The module GRIDGEO produces regular grids and packs, but up to GeoDict 2021, it did not include microstructures that aim especially at additive manufacturing. In GeoDict 2022, GRIDGEO was extended by a wide range of regular structures, which you can use as basis for your material made by additive manufacturing. First, there are the STRUT-BASED lattices. They are composed of periodicity cells, which can be repeated as many times as you wish. You can define the size of the periodicity cell and its number of voxels per side. You can also define the diameter of the struts at two different locations, in the center of the strut and near the node. And there are triply periodic minimal surfaces. They come in square or round shapes, and they can be manipulated by thresholding. For the structures you can see here, an upper and a lower threshold was defined. Next, I will introduce you to the benefits of downsampling and a user-defined downsampling factor. Why do mechanical simulations sometimes take that long? One reason is that many models of microstructures have very delicate features but must still be large to be representative. That leads to a high number of voxels and thereby a long runtime. In addition, mechanical simulations are often complex and do not use just linear elastic material behavior, but also plasticity or even damage. To solve those problems, the solver needs more time. So how reduce the runtime? Decreasing the size of the model is not an option because you want it to be as representative as possible. And you also cannot give up the complexity of the material behavior. The good news is that GeoDict offers you a possibility to reduce the number of voxels without reducing the size of the model, downsampling. And this functionality reduces the runtime tremendously. But what is downsampling and how does it work? Downsampling means that 4 by 4 by 4 voxels are combined into a single voxel. This reduces the number of voxels and thereby runtime and memory consumption significantly. In GeoDict 2022, one can also choose a downsampling factor of 2. That means that 2 by 2 by 2 voxels are combined into 1 voxel. Downsampling has a big advantage over just decreasing the resolution of your model. The material law in a downsampled voxel is a combination of the material laws of the original voxels. So both materials are considered during simulation, whereas in a coarser model each voxel has only one material law and information is lost. To show the advantages of downsampling, I determined the stiffness tensor of a rhombic dodecahedron with elastodicts phi math vox. This structure is, by the way, one of the new STRUT-based lattices in GRIDGEO. The structure had a size of 800 cubed, the struts a diameter of 16 voxels, and as a material aluminum was chosen. The simulation ran on my workstation at the office. You can see that the results with downsampling factor 2 are almost identical to the results without downsampling. A downsampling factor of 4 leads to a deviation of 16%. But the big question is, how much time does downsampling save? In this case, a factor of 2 reduces the runtime by 90%. So instead of waiting an entire morning, just go for a coffee and a quick chat and the simulation is done. When you choose a factor of 4, there is no time for a chat left. Just grab a coffee and when you come back, you can look at the results. Moreover, downsampling significantly reduces the memory consumption, by 85% for a downsampling factor of 2 and by 98% for a downsampling factor of 4. Those results show that a downsampling factor of 2 is often a really good choice. Still, you should compare it once with a simulation without downsampling before you run an extensive parameter study. If you look for a quick estimate, or you want to do more qualitative parameter studies that show tendencies, then a factor of 4 is a very efficient approach. And it can also be an option if the structure does not fit into your memory otherwise. Now I am going to show you another way to improve your mechanical simulations, the conjugate gradient solver for nonlinear simulations. Up to GeoDict 2021, Newman series was the only solver method available for nonlinear problems. Conjugate gradient was only available for linear problems. In GeoDict 2022, the conjugate gradient method is available for nonlinear simulations as well, and that comes with two main advantages. First, the conjugate gradient method is often faster, and second, it is more precise in many complex cases such as damage. First, let's look at a rather simple case. We simulated a glass fiber reinforced polyamide 6, which was loaded perpendicular to the fiber direction. For the polyamide 6, a plastic material law with exponential hardening was chosen. All three different solver methods were compared for this case: conjugate gradient, memory efficient conjugate gradient, and Newman series. Moreover, two different tolerances, tolerance is the stopping criterion, were used, 10 to the 3 and 10 to the 4. In the diagram you can see that all settings lead to more or less identical results except for one: Newman series with a tolerance of 10 to the 3. Then let's look at the runtimes. There the results are again quite similar. And you might wonder why I told you on the previous slide that Newman series is slower. In this case, the pure runtime is not. It is even faster for a tolerance of 10 to the 4. But the result of Newman series with a tolerance of 10 to the 3 is not as good as the results of the other solver methods. So to get the same results, you need to go with a tolerance of 10 to the 4, and that takes longer than conjugate gradient with a tolerance of 10 to the 3. So in this simpler case, you can see some weaknesses of Newman series, but overall it works quite well. In really advanced problems, such as the prediction of damage in composites, conjugate gradient leads to more precise results. In this slide you can see the simulation of a glass fiber reinforced epoxy resin. The white fibers go into the image plane and blue is the resin. In red you can see cracks in the resin. To provoke failure in the polymer of a composite, you must usually load it under a direction which is not parallel to the fiber direction. In this example, tension was applied under an angle of 30 degrees to the longitudinal direction of the fibers. And here you can see that the conjugate gradient method leads to more realistic results. In both methods, failure starts at stress concentrations where fibers are near to each other, but only the conjugate gradient method can deliver a proper crack. And if you look at the runtime, you can see a huge difference. While the simulation with Newman series takes 161 minutes, conjugate gradient does the job in just 6 minutes. This example shows that Newman series is not the method of choice for composite damage. With this beautiful opportunity at hand, we decided to face a more tricky challenge. In the composite industry, one of the most difficult topics is the joining of composites and metals. One reason is that the strength of the joint is difficult to predict. Our partners at the Leibniz Institut für Verbundwerkstoffe, that translates to Institute for Composite Materials, are among the leading experts in the joining of fiber-reinforced thermoplastics and metals. These processes are developed for different applications, for example joining composite car body parts to a metal car body. On the right, you can see a body in white which contains a demonstrator part, a composite roof carrier to which metal brackets are attached by laser and induction joining. The researchers at the Institute approached us with a very interesting question. They made hybrid joints between glass fiber reinforced polycarbonate and steel. To improve the adhesion, the steel surface was grooved by a laser to increase the surface and to promote mechanical clamping. In this way, high-strength joints can be produced, but this approach comes with a major challenge. The failure mechanism is really complex and difficult to understand, and standard tests, such as lab shear tests in a tensile testing machine, deliver a maximum load and a broken specimen, but no hint towards where failure started, in the joining zone or in the laminate. Micro-CT scans of the joining zone are not possible because the metal outshines the polymer. At the Institute, they even were able to get a better look into the material by making oscillating tests and stopping them before total failure occurred. The cracks are visible in the micrograph on the top, but can simulation tell where the crack started? We then simulated the failure in the joining zone. As we had no micro-CT scan, we generated the model based on a micrograph. For the glass fibers and the steel, a linear elastic material law was chosen. The polycarbonate is a macrolon, and a damage law was fitted to a stress-strain curve from the datasheet. In the video, one can see that the crack starts between the two layers of fibers. It then spreads into the fiber layer near the joining zone. The same failure mechanism can be observed in the micrograph on the left, but only the simulation can tell that the crack started between the fiber layers and not in the joining zone. If you want to learn more about composite simulation, we have the perfect event for you. The Leibniz Institut für Verbundwerkstoffe hosts a multi-scale simulation day, which features talks of researchers from the Institute, from our CEO Andreas Wiegmann, from me, and from partners of both Math2Market and the Leibniz Institut für Verbundwerkstoffe. The talks will cover topics from mechanical simulation and digital prediction of the permeability of textiles. The event is held online, the participation is free of charge, and you can just go to their website to register. If you have trouble finding it, just write us an email. So I think this will be a very interesting event if you want to learn more about composite simulation on various scales, and we would be happy to welcome many of you there. From complex simulations, we now move to complex modeling. I will show you how to make a digital twin of a metal foam. As basis, we used a micro-CT scan of a metallic foam. The foam has a solid volume fraction of 17% and triangular struts. First, we identified the pores in the foam with GeoDict. The pores at the boundaries were omitted as they would falsify the statistics. For the modeling, the most important information is the pore diameter distribution that you can see on the right. Based on the pore diameter distribution, we built a digital twin in FoamGeo. We used triangular struts and set a fixed solid volume fraction. Those two functionalities are new in GeoDict 2022. Here you can see the images of the segmented scan and its digital twin. To check whether the twin matches the segmented scan, we compared the strut and the pore diameters. In the diagrams you can see that they both fit quite well. The pore diameters are even more alike than the strut diameters. That is no surprise, as we defined the pore diameters in FoamGeo. The strut diameters were derived from the combination of pore diameter and given solid volume fraction. We also compared the permeability tensors of both scan and digital twin, and here you can see that they match as well. Based on the first digital twin, we started to change the solid volume fraction. we made a twin with a solid volume fraction of 10%, 13%, 17%, and 20%. The pore diameter was kept constant. In the left diagram you can see that this really is the case. But if the pore diameter does not change, something else must. And this is the strut diameter. On the right you can see that the strut diameter grows with increasing solid volume fraction. And now you can also analyze the influence of the solid volume fraction on other properties, such as the permeability. Here you can see that an increase in solid volume fraction leads to a decrease of the permeability. That, of course, goes hand in hand with the reduced flow velocity in the twin with the highest solid volume fraction compared to the twin with the lowest solid volume fraction. The electrical conductivity, on the other hand, increases with increasing solid volume fraction as there is more solid material to transfer the current. And the same is true for the Young's modulus. Of course, more solid material means a stiffer structure. Last but not least, I will show you new post-processing functionalities in FIBERFIND-AI on the example of a composite scan. On the left you can see a scan of a long fiber reinforced polymer. This scan was segmented in import GeoVol. That leads to the three-dimensional model of the segmented scan on the right. Then FIBERFIND-AI was used to identify the fibers in the segmented scan. Thanks to FIBERFIND's trained neural network, every fiber in the segmented scan can be labeled. The labeled fibers are then analyzed and statistics of the fibers can be derived, such as the fiber diameter distribution, the fiber orientation, or the curvature. Here you can see the segmented scan. And as you can see in this video, there is something going on in the center of the structure. To get a better impression of what exactly is going on in the center of the structure, a layer-wise analysis of the fiber orientation is done in FIBERFIND-AI. In the diagram on the right, you can see that the fiber angle to the x-axis changes throughout the thickness of the structure. In the center, the mean fiber angle reaches a maximum of more than 45 degrees. In GeoDict 2022, this layer-wise analysis is newly available for fiber length, diameter, curliness, curvature, center of mass, and angle to x, y, or z axis. Here you can see again that the layer-wise analysis of the angle to the x-axis confirms what one could see in the structure. Fibers are oriented differently between around 1.5 to 2.5 mm in thickness direction. To get an even better look at this middle layer, we used another new feature of GeoDict 2022. It is now possible to threshold the results in FIBERFIND-AI by the value of certain properties, namely fiber length, diameter, curliness, curvature, center of mass, and angle to x, y, or z axis. In this case, the threshold was an angle to the x-axis of 25 degrees. Then the fibers are segmented into two different material IDs. That means that you will get every statistic for those material IDs separately. And you can load a structure in GeoDict in which the two different fiber types are distinguished. You can see that on the right. All red fibers have an angle to the x-axis larger than 25 degrees. It becomes quite obvious that there is a massive amount of them in the center. And they are not just misaligned, but form some kind of vortex. This can often be seen in parts manufactured in processes such as injection molding or compression molding, where flow velocity and the temperature of the melt show a gradient throughout the thickness. And here you can see a video where we slide through the thickness of the material. So you can see many fibers which are aligned with the x direction, but there are more and more misaligned fibers, and now you can see this vortex in the center. Then you get more or less a white mixture, and now you have more aligned fibers again. And you will see as we approach the other end of the structure, there will again be more red fibers. And with this nice video, I want to end my presentation. Thank you very much for your attention. If you have any questions, feel free to ask, either now or write me an email later on. You can also post questions and discuss with our experts and other users in our new forum. So if you feel more comfortable there, have a look. And I hope to welcome many of you in the Digital Materials R&D workshop held by my colleague Aaron.